Okay, let's move on by talking about some problems associated with buffer systems. So this first one is going to use the same example that I used in the previous slides. The acetate buffer is used in biochemical studies of enzymes and other chemical components of cells to prevent pH changes that might change the biochemical activity of these compounds. And as it turns out, proteins are exceedingly sensitive to pH changes, and they can change the three-dimensional conformation of a protein very, very significantly by minor changes in pH. Calculate the pH of an acetate buffer system that mixes 0.1 molar acetic acid with 0.1 sodium acetate. And so first of all, you have to determine the change in direction, which we'll show in just a second, and then do the calculation as we've done before. And so let's take a look at how we would do that. Okay, we've done this before, but I'm going to write this down anyway. We have acetic acid, which looks like this, plus water, goes to form the acetate ion. Now there are various ways you can write the acetate ion in acetic acid, and if you write it different than I do, that's okay. And the Ka for this, as it says, is 1.8 times 10 to the minus 5. Now what it gives you here is it gives you the concentration of acetic acid, 0.1, and the concentration of the acetate ion, 0.1. And like I said, buffers in general are a combination of a weak acid and its conjugate base, which is what has happened here. And so initially, when we mix these two things together, there's no hydrogen ion. We don't have to worry about that. The change is going to be, we're going to end up with some amount of acid, hydronium ion. We're going to end up adding a little bit to let's do it this way, plus X, and then we're going to subtract from this. So at equilibrium, this is going to be 0.1 minus X, this is going to be 0.1 plus X, and this is X. And so we have 0.1 plus X times X divided by 0.1 minus X. And that's all going to be equal to 1.8 times 10 to the minus 5. Okay, again, this is a very large number compared to this, so we can drop X from this and we can drop it from that. And basically we end up with X equal 1.8 times 10 to the minus 5, approximately. And so the hydrogen ion concentration is approximately this. If you put that in your calculator, the pH of this solution is going to be 4.77. Or excuse me, 4.74. Sorry. Now, the next problem here, and I'm not going to blow this up, is to take this same buffer system and add 1 milliliter. You've got 100 milliliters of this buffer system that has this pH, and we're going to add 1 milliliter of 0.1 molar sodium hydroxide. So how does that affect the pH? Now remember, back here in this example, we only added 1 milliliter of 0.01 and we changed the pH from 8 to 4 in an unbuffered solution. So if we add 1 milliliter of base to this, what effect is it going to have on this? So how do you go about doing this? Actually, I am going to blow this up so you can see this diagram. What you have to do is take the volume that you've added and calculate the moles of sodium hydroxide you're adding, the volume of the buffer, and the initial moles of acetic acid, and also the effect of that on additional moles of acetate, and use those constant, and then what's left an unreacted acetic acid. When you add this hydroxide, what's going to happen is it's going to combine with this to form a little bit more of the acetate, and it's going to leave a little bit less acetic acid behind. Then you used a little bit less and the little bit more and the new volume of 101 to calculate these two concentrations, and then you put these new concentrations in your situation and do the same thing again. Okay, so you have to start out with this and then do this, and then it comes down to the same calculation we've done time and again. So let's see what this looks like. And let me roll this up. Well, actually, I'm going to leave it like this so we can see the equation. So we're going to add, first of all, it says we need to calculate the moles of acetic acid, or sodium hydroxide. So we're going to add 1 milliliter of 0.1 molar. So that's 1 milliliter, or 0.001 liters times 0.1 moles per liter. So we ended up adding 1 times 10 to the minus 4 moles of hydroxide in the form of sodium hydroxide. So you take 0.001 times 0.1, and you get 1 times 10 to the minus 4 moles of hydroxide, sodium hydroxide. So that's how much you're adding. The second step is looking at how much initial acetic acid you have. So I'm just going to write AC because it goes faster. You have 100 milliliters, or 0.1 liters, times 0.1 moles per liter. So that's going to be 1 times 10 to the minus 2 moles of acetic acid. Now when this reaction occurs, it's going to take away from that much, away from this, and add it to this. So you had, so the new AC is going, this calculating the, so we have the initial moles I've just calculated. So the additional mole, the unreacted moles of HAC is going to be 1 times 10 to the minus 2 minus 1 times 10 to the minus 4, which is going to be 9.9 times 10 to the minus 3 moles. And the added acetate is going to be 1 times 10 to the minus 2 plus the same 1 times 10 to the minus 4, and this is going to be 1.01 times 10 to the minus 2 moles of acetate. So now the new concentration for acetic acid is going to be 9.9 times 10 to the minus 3 over, now this is the moles, 101, remember you're adding 1 milliliter, so it's going to be 0.101 liters. And if you do the math here, the new concentration is 9.8 times 10 to the minus 3. And the new concentration for AC is going to equal 1.01 times 10 to the minus 2 over 0.101, which is going to be, it's going to go back to 1 times 10 to the minus 1. So we take these numbers and we put them in our, these are our new concentrations for these two things, and then we put them back in our original Ka equation. Our original Ka equation had X for the hydronium ion concentration, and it's going to be 1 times 10 to the minus, or 0.1 minus X divided by 9.8 times 10 to the minus 3 minus X. 1.8 times 10 to the minus 5. And so again, you can disregard these two, and you end up with 0.1x over 9.8 times 10 to the minus 3. I'm sorry. 10 to the minus 2 here. and that's going to equal 1.76 times 10 to the minus 5. And if you do the pH calculation on that, you get 4.75. So it went from 4.74 to 4.75. Notice that the addition of fairly strong acid had virtually no impact. And that is exactly how buffers work. And that's exactly what I wanted to show with this calculation. Now let's talk for a minute about something called buffering capacity. The buffering capacity is the amount of acid or base that can be added to a given volume of a buffer solution before the pH changes significantly. You can always overwhelm a buffering system. You can add a little bit of acid, even a little more than you would imagine, but if you add enough, you can exhaust the buffering system such that the pH will change dramatically. And here's a diagram of how buffers work, and you can see that good buffers generally have an equal amount of both components, that is the weak base or the weak acid and the weak conjugate base. They're generally, weak acids and their salts have pHs less than 7, and weak bases and their salts have pHs greater than 7. And the graph is an illustration of the pH change with the addition of various amounts of sodium hydroxide. And you can see that you can add 100 milliliters to this system before it is exhausted. And at that point, it becomes exhausted and the change is rapid. The Henderson-Hasselbalch equation can be used to calculate an estimate of a buffer's pH. And the Henderson-Hasselbalch equation looks like this. The pH is the pKa of the situation plus the log of the concentration of the conjugate base over the log of the conjugation of the concentration of the weak acid. So you can use this equation instead of just putting the numbers in for, as we did in the previous slides, to make an estimate of the pH of a various buffer. Now we'll finish up by talking and doing one problem or two problems in acid titration, acid-base titration. Acid-base titration is when you add a base to an acid until the pH changes to equivalent 7. And here you can see on the left is a strong acid, and it has a very abrupt change when you add sodium hydroxide. And that point of change at 25 milliliters tells you the concentration of this strong acid if you know the volume. On the other hand, the equivalent point of a weak acid is not going to be exactly 7, as we said before. It's going to be slightly above 7 because the conjugate base of a weak acid is a strong base and you have a slightly basic solution. So you carry out a titration of 25 milliliters of 0.1 molar acid and you get 25 milliliters of 0.1 molar base. But if you do the similar titration, the equivalence point is not exactly 7. And here are some various indicators. Indicators are used to show they're either weak organic acids or weak organic bases that change color depending on the pH. And this chart just shows several indicators that are used. We used to use phenolphthalein, which is third from the bottom. You can see that its changeover point is actually fairly high at 9. The graph shows that the titration curve of a 25 mils of acetic acid with 0.1 molar sodium hydroxide. The titration curve for a strong acid and a strong base will have an equivalence point at 7, but a weak acid and a strong base, the equivalence point is actually in the range for phenolphthalein. So let's do a couple of problems to look at how you do acid-base titrations. If it takes 54 mils of 0.1 molar sodium hydroxide to neutralize 125 mils of hydrochloric acid, what is the molarity of hydrochloric acid? This is actually a very simple calculation, and what you do is you use the equivalency of the molarity of one times its volume is going to equal the molarity of the second times its volume. And so in this case we want to know the molarity of this, so the molarity of one, the acid, is going to equal the molarity of the base times its volume divided by the volume of the acid. So it's going to be 54 times 0.1 divided by 125. Now you can use 54 and 125 as long as they're both in milliliters. Or you could put 0.0, if you want to use liters to be technical, you can do it this way. And if you do this calculation, you get 0.043 molar HCl. The second introduces the idea of a diprotic acid. So for each mole, you're going to produce 2 hydrogens, and you have to take that into account. And so for the molarity of the acid in this case, it's going to be the molarity of the base times its volume divided by the molarity of the acid, but you're going to have times 2 because you're producing 2 hydrogens at each point. So that's going to equal 50 times 0.5 divided by 2 times 125. And that's going to equal 0.100 molar sulfuric acid.